Yesterday, we loosely defined momentum as how hard it was to stop something. We know that that's not the technical scientific definition of momentum, but it's a good way for us to understand what momentum is, right? Something that's hard to stop has a lot of momentum. Now, we also identified two factors that increased the amount or the difficulty in stopping something. Those two factors were mass and velocity. The heavier something is, the harder it is to stop. The faster something's moving, the harder it is to stop. Both of those factors, mass and velocity, increase how difficult it is to stop something, so they both contribute to the momentum of an object. A train has a lot of momentum. How come? It doesn't matter how fast it's moving. As long as it's moving, a train has a lot of momentum because it's got a lot of mass. A bullet has a lot of momentum. Not because it's got a lot of mass, but because it's moving very, very fast. So two different things can be difficult to stop for two different reasons, but in the end, it both boils down to they both have a lot of momentum. That's versus inertia, which is the tendency to resist a change in motion. It's a subtle difference, but it is a difference here. Momentum, how hard it is to stop something. Inertia, you could say how hard it is to stop something, but also how hard it is to start something, or even how hard it is to make something speed up or slow down. It's a tendency to resist any change in motion. And that, of course, depends only on mass. This is what we focus on in this unit, momentum, not inertia, but I just wanted to differentiate between momentum and inertia so you wouldn't think that they were the same thing. We saw our data sheet, bottom left-hand corner, we saw a category called momentum and energy, and of course our first equation that we did this year was P is equal to m times v, lowercase p with a little arrow over top of it. What did the arrow mean? What was the significance of that? It's the direction, right? Momentum is a vector. M stands for mass, good. And what are the units for mass? Good. And V stands for velocity, good. And what are the units for velocity? Meters per second, good. If I had 20 centimeters per second and I wanted to convert that to meters per second, what would I do? Divide by 100. I asked that question in the last class. Somebody said multiply by 100. I make that mistake sometimes. I mess up on whether I multiply or divide. That's okay. It is divide, by the way, you're right. But if you multiply by 100 and get 20 or 2,000 meters per second, you just got to take a step back from it and see if it's realistic, right? 20 centimeters in 1 second. Is that the same thing as saying 2,000 meters in 1 second? Like, if I got something that's going 20 centimeters in 1 second, is that the same thing as saying an object is going from here to the bottom of the hill on 32nd Street in 1 second? Clearly no. So if I made a mistake with multiplying by 100, that's okay. Just make sure that you recognize whether it's realistic or not, and if it isn't, then just make sure you change it. So in fact, we are going to divide by 3.6, just like Kelly said. Sorry, not 3.6, but 100. Divide by 100. And that gives me 0.20 meters per second. Good? Now I just gave away my next one. 72 kilometers per hour. Converted to meters per second. What do I do here? Divide by 3.6. You can multiply by 1,000 to get meters and then divide by 3,600 to get seconds. Or the shortcut is just divide by 3.6. And that gives me 20 meters per second. Is that realistic? Sure it is. If you had have guessed wrong and multiplied by 3.6, see what you would have gotten here. 72 times 3.6 is 259. 259 meters per second. Is that realistic for 72 kilometers per hour? Like 72 kilometers per hour is your speed on McLeod Trail in Calgary. Right? Are you going to go 2.5 football fields per second on McLeod Trail in Calgary? Like, you're approaching the speed of sound here. Right? So it's not realistic if you got 259. If that happens, that's okay. We just change our guess to divide by 3.6, and we end up with a realistic answer, so that's what we go with. All right? Good? Okay. We'll leave it there, guys. We'll just take a look at our homework now. Questions 5 to 8. You guys asked me to go over 7 and 8. Nobody needs 5, 6? Okay, 7 and 8 it is. Number 7 says a 1.00 kilogram rock is thrown up into the air from ground level at a speed of 8 meters per second. The ball travels up to a max height, then returns to the ground. Calculate the rock's momentum as it strikes the ground. What do we got here? M is 1.00 kilograms. Hey, is there anything I should red pen here? Remember the red pen? The whole point of that was to identify things that could lead to a silly mistake, like a sign or direction or like a conversion or anything like that. Anything? Just, okay. Returns to the ground. By the way, this is not a hard science of red pen, right? Different people may red pen different things, right? Whatever's going to might lead you to a silly mistake is what you should underline or circle with a red pen. Okay, so some of you might say, I don't need to do that. That's fine. Some of you might say it's helpful to draw attention to that. Okay? All right. So our mass is 1 kilogram. We're launching at a velocity of 8.00 meters per second. It says a speed, but we know it's being thrown upwards, so I'm going to call it a velocity. Ball travels up, max height, returns to the ground. What's the momentum as it strikes the ground? By the way, that's VI. I want to find PF. And just like a couple other questions we've had, PF is M times VF. M is 1.00 kilograms, but I don't know what VF is. We talked about this a little bit when I was giving the answers. If I launch it at 8 and it goes up and stops and it comes back down to the same height that I launched it at, then how fast is it going to be moving? 8. I mean, think about this. It decelerates as it goes up at 9.81 and then it stops. And then what does it do on its way back down? It accelerates at 9.81 over the same distance. It's got to be moving the same speed when it reaches the bottom. So what is the final velocity? No, not 8. Negative 8 meters per second. Or you could say 8 meters per second downwards. Now, if you have trouble with that, the logic on that, all we have to do is say VF squared is equal to VI squared plus 2AD. A little bit more work, but it works. VF is the square root of 8 squared plus 2 times 9.81, neg 9.81 times negative, what is the max height? I don't know. Yeah, that's right, whatever you want. It doesn't really matter, right? That probably wouldn't be the way to go there. Let's see. What would work for us here? You could say D is equal to VF, VI plus V. No, that's not going to work either. Sorry, MGH, but that's potential energy. Oh, okay, so you're saying MGH equals 1/2 mv squared, and then find the height. Okay, yeah, that would work. Yeah, that would work. And then VF squared is equal to VI squared plus 2AD, using the height as the displacement, but make it negative. Yep. Probably easier just to recognize that it's -8 from the top, though. Yeah, cool. That's right. Yeah, that's you're right. Actually, I was looking at the trip up, but if you look at the entire trip, you're absolutely right. We don't need to bother going through all that process, right? VF squared is equal to VI squared plus 2AD. And if you're looking at the entire trip, displacement is 0 because you're back where you started. And then VF is just the square root of VI squared. Yeah, you're right. That's what I mentioned before, right? So I'm analyzing the trip up. I don't know what D is. I'd have to find it, like we were talking about a second ago. But if I analyze the whole trip, which makes sense to do, then D would be 0. Okay, do the math here. You know what? I think you guys are smart enough to do this without your calculators. Okay, well, some of you are. 1 times -8 is -8.0 kilograms meters per second. -8.00, actually, isn't it? 3 digits. Number 8. This one This one is close to the same, right? The wording of this is close to the same. It says the 1.5 kilogram rock is thrown up into the air from ground level, reaches a max height of 7 meters, then returns to the ground. What's the rock's momentum as it strikes the ground? What's the same about this question? Rock gets thrown up into the air. Right? What's different about it? It gives us the height, and it doesn't give us the initial speed or velocity, right? So we're going to have to tackle it a little bit different because of that. Anything red pen here? No, I don't think so. Maybe returns to the ground. Maybe again, depending upon what you think you'll make a mistake on. Let's write down some givens here. 1.5 kilograms is our mass. We don't know what VI is. We want to find PF. What do you want to call this? 7 meters. Height, displacement, either one really, right? I'm going to call it displacement because you guys don't seem to really like using the EI equals EF thing as much as the VF squared. I'll tell you what though, I'm going to put a little star by this. And the reason I'm going to do that is because that displacement is not the displacement over the entire trip. I want to find the velocity, or sorry, the momentum when all is said and done. But the displacement at that point is not 7. So I'm going to star it so that we kind of remember that, like when we're dealing with that displacement, we're dealing with kind of half the trip, right? Make sense? Okay, I think what I want to do here to find VF is to say VF squared is equal to VI squared plus 2AD. Oh, you know what I think I'm going to do? Since I want to find the speed as it reaches the ground, I'm going to actually make my displacement -7, -7, and analyze not the trip up, but the trip down. Does that make sense? Okay, so VF is what I'm looking for there. What's VI if I'm analyzing the trip down? 0, because it goes up, slows down, and stops, and then speeds up, and reaches VF. So VI on the trip down would be 0 meters per second. 2 times -9.81. And D would be -7.0. So we square root that to find what VF is. And we get 11.719. What did I just find? Yeah, VF. What is that called, though? Not in a symbol, but in a word? No. Close, though. That's the mistake that I was trying to get you to make there, that I was sucking you into. It's not final velocity. Final speed. Right? We just found final speed. What's the final velocity? -11.719, right? Make sense? So we're going to say PF is equal to M times VF, which is 1.50 kilograms times -11.719. Or you could say 11.719 downwards. Okay, multiply that by 1.5. And we get -17.6 kilograms meters per second, or I could say 17.6 down. Good. How many people got both of those questions, 7 and 8? Okay, good. Okay, especially number 8, I thought is tricky there. So if you got those, then that's good. You're starting off really well. If you didn't get them, that's okay. It's not like you're not like going to fail or anything because you missed one or both of those questions. But okay, I want to do one more example today, and that will likely be it for the day. One more example questions, and we'll have you work on some questions. But that's not the one. This is the one. Number 3. This one says the momentum of an object is 200 kilograms meters per second. What does the momentum become if the mass is doubled, but the velocity is reduced to 1/3 of its original value? What's So here's, like let me get this straight here. I want to find the momentum of an object, but I don't know what its mass is, and I don't know what its velocity is. All I know is that I've changed the mass by this factor, and I've changed the velocity by that factor. Sorry, go ahead. Yeah, in some of these situations you can do that. I want to teach you a more general way of doing it, though, to tackle a more general question here. I want to use what I call variable value changing. Okay, that's just my name for this. Okay, my technique is essentially the same as other people's technique, but there's no real name to it. So I call it variable value changing. We're changing the value of variables without knowing what they were to begin with. So here's what I want to do in this technique that I call variable value changing. I want to find a relevant equation. Okay, my relevant equation is P is equal to m times V. Or if I wanted to calculate the momentum and I had numbers, then this is what I'd use. So let's write that down. If you got mass, you got velocity, you want to find momentum, this is what you do. And then I want to put a little subscript in there. My original momentum, this is what it starts with as, is equal to m times v. But it's also equal to, you can see here, it's 200 kilograms meters per second. So what have I done so far? I've basically just written down what I already know. I've written down that my original momentum is 200. We're told that right in the question. I've written down that my original momentum is m times v. We're told that on my data sheet, right? So nothing new here yet. Now it's time to do something a little bit new, though. Now I want to say my new momentum. After I make my changes, after I double the mass, but I reduce the velocity to 1/3 of its original value. I'm going to let you in on a dirty little secret right now. Don't tell anybody. When I told you the equation for momentum is m times v, I lied. The equation for momentum is mass times velocity. We represent it as m times v. The equation for speed is distance over time. We represent it as d over t. But we can represent it any way we want, as long as we fundamentally have the correct equation. Does that make sense? Like if I called mass x, then I could say momentum is x times v. That would be correct, right? As long as I know the real equation is mass times velocity, we can represent it any way we want. We just choose to represent it m times v because it's convenient to do that. Make sense? Okay, well right now I'm going to represent it slightly different. It's not going to be m times v. My new momentum is not represented by m times v. It's represented by 2m, because I doubled what the mass was, times 1/3 v. Does that make sense? It's still mass times velocity. Look, this is mass. It's just a different mass than it was before. It's twice what it was before. This is still velocity. It's just a different velocity than it was before. It's 1/3 of what it was before. So it was m times v. Now it's 2m times 1/3 v, which is still mass times velocity. Right, Cole? So now what I want to do is pull the 2 and the 1/3 out front. I'm going to make it 2/3 m times v. Now look at this. It's 2/3 m times v. But what's m times v? Who's got this? What's m times v equal to? 200. Look. M times v is 200. So let's just say it's 2/3 of 200. Does that make sense? Sorry? What's the number there? 2/3 of 200? 133? Is that okay? Pick your relevant equation and then set it equal to whatever its original value is. And then write down a new equation. It's still mass times velocity, but my symbols are different. Instead of mass being m, now my symbol for mass is 2m, because I doubled it. My symbol for velocity isn't v, it's 1/3 v, because I cut it by a factor of 3. And then I pull those numbers out in front, multiply it by whatever the original value was, and I'm done. As I look out at your faces, I think I want to give you another one to do yourselves right now. I wasn't going to do that. I was just going to set you to work on some check and reflect questions from your textbook. I think I'm going to give you another one of these first before I do that, okay, just to make sure that we're on the right track here. So, because I hadn't planned to do this, I'm going to make this one up on the fly. I'm going to say the momentum of an object, let's make it a, let's say the momentum of an object is increased by a factor of 3. The mass of the object is reduced to 1/2 of its original value. If the original velocity was 10 meters per second, what is it now? Or what is it after these changes are made to it? Give this a try yourself. I'll give you about 2 minutes to work on it, and then we'll take a look at it as a group before I let you work on those check and reflect questions. Okay, let's have a look. The momentum of an object is increased by a factor of 3. The mass is reduced to 1/2 of its original value. The original velocity was 10. What is it now? Listen, the relevant equation here is V is equal to P over M. Right? P is equal to M times V, but I got to rearrange it to get V is equal to P over M. This is my original value, and it's 10, right? 10 meters per second. Now, I'm going to write down my new value, or my new equation. It's still momentum over mass, but momentum isn't P anymore. Momentum would be, I'd call momentum 3P. See? 3P? Oh. What's mass become? 1/2, right? Oh, I know exactly what you did. Or exactly what everybody else did. What's 3 divided by half? It's 6, right? Same as saying 3 times 2 over 1. Right? When you divide by a fraction, you multiply by the reciprocal. What do you guys say in math class? You kiss and flip? Sorry? Copy, kiss, flip? I always learned it as just multiply by the reciprocal. So if it's 1 over 2, multiply by 2 over 1. That becomes 6 over 1, or 6 times P over M. And of course, we know that P over M is 10. So we're just going to say 6 times 10 is 60. Should be 60.0 actually, kilograms meters per second. Good there? Guys feeling a little bit better about that? Okay, I'm going to give you some what's called check and reflect questions from a textbook that you don't actually have. You get a couple options for this textbook. You can just look at the questions on the screen, because I'll always put them on the screen. B, you can actually go to the library and pick up a textbook. Not right now, but just sometime, sometime you have a chance to stop by and pick up a physics textbook. Or, this is what I suggest you do, go to Google Classroom and go to the About tab, scroll down under the About tab, and all the chapters that you need are there. We've bought a license for that textbook. Okay, we can legally allow you to use the electronic version of the textbook. And man, is it so much, in my mind at least, is it's so much easier than carrying around this big, thick, heavy textbook. But whatever works for you, okay? We have physical textbooks, we have the electronic version, whatever works for you. And I'll also, in class, always put it up on the board. So here's what I want you to work on today and for the weekend. Questions 1 to 2 on page 453 of your physical textbook or your electronic textbook or your textbook that's up on the screen right now, however you want to do it. Questions 1 to 2, 5 to 9, 11, and 13 to 16. All right? It is 11:12. You have the rest of the class, which is about 12 more minutes to work on those questions.